Going back to lecture 23, when we're dealing with the instantaneous rate of change, we talked about something very interesting, which was lim, and then we had x here, and then we had a little arrow, and then we have an a. And then we kept using this thing, and then we dropped it at some point, and after dropping it, and then we realized that actually the meaning behind this thing is beyond just writing this whole thing actually, because this is just saying the limit, and then this arrow here is saying I pick a value that is so close to a, so close to a that the computer cannot pick the difference. So that's what we were actually dealing with. But now, can we actually formally define what is a limit of a function, and then actually look at the tips in the couple of lectures? We'll look at the tips on how to actually evaluate limits, because it's not always so strict to actually deal with the evaluation of limits. So the first kind of limits that we'll look at here is the finite limits of rational functions. So we'll start to look into that, and then from there we will actually go and look at one-sided limits, and then from one-sided limits we go to limit rules, and then from there we go to infinite value limits, and then yeah, I think that's how we will go with this. First of all, I want us to actually define, so that I don't end up define what is a limit and the most important terms and how we go about it. Before I can waste more time trying to write the whole definition, I'm going to pause a little bit, and then after that I write it, and then I can explain after writing the whole definition. This definition is just saying this. Suppose f of x is a function, and f of x is defined close to the point x is equal to a. It's defined everywhere close to that point, right? And it is either defined at point A or not defined at point A. That's what this is saying, right? Then the value L is said to be the limiting value of that function as x approaches a. If so, there is a condition for this to call it the limiting value of this function, and that condition is if whenever I take the difference between L and f of x, right? If I take the difference between L and f of x, as I keep picking values that are so close to a, I make that difference so small, right? So small, right? Then I will say that this is the limiting value if the difference between these two can be found so small as I keep picking values here, that values of x that are so close to a. But to write this whole thing, we just say the limit as x, we have this arrow here. This is the limit as x approaches a of f of x is equal to L. Or alternatively, we can say that L is the limiting value of f of x as x approaches a. It is a limiting value of f of x as x approaches a, meaning that this is the limit under the assumption that I can pick a value so close to a such that the difference between L and f is so small that the computer cannot pick it up. Alternatively, we usually say f of x approaches L as x approaches a. This is just all the wording there is to it. But let us look into functions here and analyze what we actually mean by this. Suppose that I have a curve here. I'm going to draw a curve. This is the Cartesian plane first. So this is the Cartesian plane. This is the Cartesian plane. Okay. Now that I have this, I'm going to draw my nice curve here. And then this curve of mine looks something like this. and at some value here, right, I have my value a here, and at this point here, right, this value here is, let's say this is L, right, and then I also have another one here. I have another curve here, and I also have another one. I want to have 3 of these things here. I want to have 3. I want to try and see if I can explain that definition and if it makes some sense or not. And then I have another curve here, which is like this. There is a hole there. And then I also have another curve here, which is like this. Of course, here there is a hole, but here there is some dot here. I'm gonna call this one here. Suppose this one is going to be N, and then this one here that comes to this point is going to be M, and then at this point here I have A, and then again here I have A, and then here I have, let me just say some M, doesn't matter. Now, what do we mean by this whole thing here? This whole thing here. We are actually saying this. Suppose that I pick a value here. If I pick a value here, so close this side, such that the difference between A and that point, remember this point is somewhere here. This is my X. If I pick that point so close, right, remember the output of A is supposed to be somewhere there. If I pick a point on the right, it's going to be so close somewhere there, such that the difference between those two cannot be seen properly. Or if I pick a point on this right and this left, and then that's going to be my X on the left, such that the difference between that point that is there, which is the output of the point that I picked, it is so close to that, such that this output of that point, remember I picked the point X, I have f of x. If I were to take the difference of L minus f of x, this one is so close to 0, right? So we say that L is actually the limiting value of this function, or we can say that the limit as x approaches a. What we mean by that, we mean that I pick a value so close to a. What is actually that value that is actually there? So if let's say this value here, let's say was 5, I pick 4, 99999999999999999, and then I plug it in F. What will be that output that is there, right? So I call that output the L. You get what I mean? So this one is going to be f of x. The limit as we're approaching a in this particular case is going to be our L there. Take note that at this point here, we don't really need to have f of a being defined. It cannot be defined, but as long as I know that when I pick a point so close, what is that value that I am close at here, which is actually the output there. Now, let's look into this. Again here, this function here, there is a hole there, which means it's not defined at that point. But if I were to pick a point so close to A, what will be the output that is so close to that hole there? So close to that hole there, what will be the output? Because if I take that output and I subtract M from it, I will get 0.0000000000000 something. We say that the limit, if this one is our f, the limit in this case, or as x approaches a, of this function f is equal to m. Even though it's not defined, we don't care what is happening there. I wanted to know what is that output that getting close to. If I pick a value so close to a, what is that output? If I pick a value on the left, remember that I will end up having a value on the left here and a value on the right there. So as I keep picking value close to A, what is that value that I keep getting closer to here? And if I pick values on the right, what is that value that I get close at there? That is actually the limit of the function. The value that I'm getting closer and closer, or the value that this function is getting closer and closer to it, that is actually the limit. It's not the value of the function, it's actually the value that this function is getting closer and closer and closer to it. Then that will be actually the limit. And then if you look into this function here, I'm going to call it f, you can see that the value of this function, because I've shaded it here, if I were to look at f of a is equal to n. But here, the function is not defined, it's only defined at this point, because when there is a hole there, you must know that whenever there is nothing, then the function is not defined there. So this curve here is not defined at that point, but because of this dot here, our f of a is going to be that output there, which is n. Right. But now f of a is equal to n. Now, what will be the limit as x approaches a of f of x? Now, what we do here is saying, if I were to pick a value that is so close to actually a, what is the output that is going to be there? If I pick another value that is so close to a, such that the difference between a and that value that I pick, which is x, is 0, what is that value that I keep getting closer and closer to it? And if you look into on the left also, if I pick a value so close to a, what is that output that I keep getting closer at? So I pick a value down here, and then I go all the way up until I arrive on the function. And then when I arrive on the function, what is that value that I keep getting closer and closer to it? When I'm going this way on the from the left and going that way on the right, if you look into this function, it's going all the way, like this is going all the way. What is that value that I getting? This function is getting closer and closer to here. As you can see here, the value that we're getting closer and closer to is m. So the limit as x approaches a of f of x is equal to m. So that is actually the limit, right? In other words, m is the limiting value of f of x as x approaches a. This arrow here is saying x is approaching a. So the m is the limiting value of f of x as x approaches a. And sometimes we just say f of x is approaching m as x approaches a. So this means approaches. So that's what we usually mean by a limit. What is the output? As I keep approaching a from both sides, what is the output that I keep getting closer and closer to here? Let me take some examples here. So I'm going to take some examples here and see what we're going to do. Suppose that I have my f of x is equal to okay. Suppose I'm saying that evaluate, right, the limit as x approaches 1 of x squared. So I want you to evaluate this. So basically, what we are saying is this: draw this curve. Okay. What we are saying draw this curve here, So we want you to draw, let me do this. We want you to draw the function y is equal to x squared. So if I were to draw this curve, it usually looks nice like this. nice like this. Of course, if I were to plug in 1 here, when x is equal to 1, and then 1 squared is going to be, of course, going to be 1. Now, I want you to find the limit as x approaches 1 of x squared. Or I want the limiting value of this function as x approaches a 1. So, if I were to pick a value so close to 1, and I go up there, and that value is there, okay, what will be that output there that is so close to this point? Let me explain again. Let's start here. Suppose I pick a point here, right? So this is my first point, x. I pick my another point on the left because we always pick left and right. This point here, the output of it will be some value there. Fine, will be a value there. But if I keep picking another point here, pick another point, from moving from this point to that point, the function is going to move from this point to that point. And if I pick another point so close to 1, the output will be moving close to that point there. I'm going to place dotted lines going all the way. Now, if I keep picking points on the left, the output will be there. So this function has moved to that point. I pick another point here, the function is moving all this way. And then I pick another point so close, the function will be moving that way. So as I keep getting closer and closer to 1 on the right and on the left, what is that value that I keep getting closer and closer to here? So if you look here, you can find out that if I, let's say for some reasons, I were to pick my x is equal to 1,000,000,000,000,000,000,000,000,1. I plug it there. So I have 1,000,000,000,000. I want to place as many zeros as I can there. The value that is so close to 1 on the right, and then I square it up. No. I'm going to place a 1 at the end. I have a 1 there. You can see that as much as I keep placing all these zeros and place a 1, the calculator is going to tell you that actually, I'm going to round off your answer to be equal to 1. So the value that we keep getting closer to on the right is a 1. If I were to pick a value on the left, so let's say 0,99999, so I'm going to place as many 9s as possible so that I'm very close to 1, and then I square it up. What will be the output? The output is 1. So the value that I keep getting closer and closer to here is just actually 1. So the limiting value of this function is a 1. That's all there is to it. That's what is this limit. Now, there are several ways on how to evaluate limits, right? There are several ways on how to evaluate limits. I want us to start with these are the examples. Let me write them blue. Now, what I want us to actually look at here is that how do you evaluate a limit whereby I am actually looking for the limit as x approaches a of f of x, right? So how do you end up evaluating this limit here? Suppose the question is saying evaluate this limit. Now, I want us to start with the case whereby if I take x is equal to a and I plug it in this function here. In other words, if I have f of a is equal to 0 over 0, how do you deal with a limit whereby if you take this and you plug it inside this function, you're getting a 0 over 0? How do you deal with that? So the first thing that I want us to do here is try to factorize. You factorize and cancel out the common factor. So this one is the first thing that you have to try. If let's say you have a limit here, that is actually, you have a limit such that if I take x and I plug it directly as it is, I get 0 over 0. The first thing you need to try, factorize and cancel out the common factor. Let me try and look at the examples. Suppose now we have 1. The question, of course, it is evaluating. I want you to evaluate the limit as x approaches 3 of x squared minus 9 all over x minus 3. If let's say we take this x is equal to 3 here, we have this 3 here, and I plug it there, I will end up having 3 squared minus 9, which is a 0. So we'll get a 0 here. So 3 squared minus 9 over 3 minus 3. So 3 minus 3 is a 0. And this is 9. 9 minus 9 is a 0. So I am getting a 0 over 0 as there. So the first thing to try out, factorize and cancel out the common factor. If I am plugging in 3 here, of course I know that I'm getting a 0. So I'm still going to have a limit as x approaches 3. X, I am going to change this. I'm going to change this, the sign of this. So I still have an x. This was positive, so I'm going to have a minus here. Because this is making this equal to 0, then x minus 3 must be one of the factors of this. Because here we have an x squared. How do you factorize a difference of two squares, given that you already know one factor? It's actually very easy, because we're going to have x squared divided by x, and you end up having an x, and minus 9 divided by minus 3, you end up having a plus 3. And then look into this part here, look into that part there, and then you'll be left with that. Let me write it down. So we're going to have the limit as x approaches 3 of x plus 3. Now, this function here, you can see that if let's say I were to choose a value so close to 3, 3, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, and then I add a 3 into it. The calculator usually round it off and say, okay, the value that is so close to 3 is actually, I'm just going to round it off and have a 3, because it can't really see the difference from this number that I wrote and 3. And then it's just going to say, okay, whatever that value you're going to pick, it is just 3 when I'm rounding it off. So you will end up saying, remember now, I'm evaluating it, so I drop the limit. So we'll just say this one, the calculator is not going to pick it up. So it's just going to say that this value here, I'm rounding it off to be just a 3 plus 3. So you end up having a 6. Look at what the calculator is going to say. It's going to say a 6. We are not saying that that value that we're plugging here is 3. We are plugging a value so close to 3, such that the calculator and the computer cannot pick it up as a different value. So that was what we are actually getting to here. Let's take another example here. Another example is going to be our B here. Our B is going to say, I want you to evaluate the limit as x is approaching a minus 3 of x to the power 2 minus 9 over x plus a 3. Now, if you look into this, of course, if I'm plugging in here minus 3 and then you square it up, it's going to be 9. 9 minus 9 is going to be a 0. And then if I'm plugging a minus 3 here, minus 3 plus 3 is going to be a 0. So the first thing to do is actually factorize. So we are this is going to be the same as the limit as x approaches minus 3 of x is good. This is going to be the same as the previous one. So we're going to have minus 3 and x plus 3 all over x plus 3. Again, this and that will cancel out, and now you will end up having the limit as x approaches minus 3 of x minus 3. And now, if you look into this, if I pick a value so close to this, the calculator is going to round it off. And then when it's rounding it off, it's not going to see the difference between that value and -3. So we'll drop the limit and have -3 minus 3, which is -6. That's how easy this thing is. And then let's try another example here. See, I want you to evaluate the limit as x approaches 0 of 2x squared minus x all over x. Now again, if I'm plugging in a 0 here, 2 times 0 squared is just 0 minus 0, 0 divided by 0. So we end up with 0 over 0. So the first thing to do or try is factorize. So we'll end up having x approaches 0 of x, because we have x everywhere. So we'll end up, if I'm taking one x out of this, I'll be left with 2x. Another x, I will end up having a 1 all over x here. This x and this x are a problem here. Let me take them out. Now we're left with x approaches 0 of 2x minus a 1. Now, if I am picking a value so close to 0, so close that this calculator cannot pick it up, and I plug it here, the calculator will round it off and say, that's just a 0. And then you drop the limit, so you'll end up having 2 times 0 minus 1, which is just gonna be 2 times 0 is minus 1, so you end up having a minus 1. That's how easy this damn thing is. And then let's try some D now. Let's try some D. If I am looking at the limit as x, suppose we're saying evaluate the limit as x approaches 3 of some f of x, right? Where this f of x of ours, I want it to be a piecewise function, because that's where we actually get to understand this whole thing. I'm going to have x minus 3, and then here when x is not equal to 3, and then here I'm going to have 8 if x is equal to 3. Okay, so this one here is only defined when x is not equal to 3, and then if x is equal to 3, the output is going to be 8. So when x is not equal to 3, y is equal to this whole thing. When x is equal to 3, y is equal to 8. That's the meaning of this piecewise function. Now, we want to evaluate the function as x approaches 3. Let's take a look into this. The limit as x approaches 3 of f of x is equal to, let me first write this, x approaches 3. Now, if let's say I want to pick a value so close to 3, remember this limit here is saying take a value so close to 3 such that the computer cannot pick the difference between 3 and that value. Now, because this value that I'm picking is so close to 3 but it's not 3, remember that if x is equal to 3, then this is the output. So if this value is not 3, so this value is close to 3 but it's not 3, which means now we end up having that function there. So our f of x when x is not equal to 3 is going to be x squared minus 9 over x minus 3. That's how we end up dealing with this. So, which means that now we're back with the limit as x approaches 3. Of course, if I'm plugging in a 3 here, I will end up having 9 minus 9, which is 0. Plugging a 3, 3 minus 3 is 0. So I have a 0 over 0. First thing is to factorize. I divide by x minus 3. This and that is the one that is giving us a 0, so I'm removing that problem here. So I end up having x approaches 3 of x plus 3. Now, if I pick this value that is so close to 3, the calculator is not going to see the difference, the computer is not going to see the difference, so it's going to round it off to 3, so we'll end up having a 3 plus 3, which is just a 6. I want you to take note of this, that every single time we are picking a value, this value we are picking is close to 3, but it's not exactly 3. So we always follow the domain that is saying not equal to. So we're going to follow that because we want to go close to 3 but not at 3. So hence we don't want this one because this one is saying at 3. So we have to pick that one that is saying not 3. So if we want something close to 3 but it's not 3, we have to pick that function that characterizes that. So that's why we ended up picking this thing up. Now, let's talk about other examples here. I have my example E now. E is saying evaluate the limit as x approaches 0 of now I have a square root of x plus a 4 here. Have x plus 4 minus a 2 all over x. I want to evaluate this limit here. The first thing that you always do is take this x is equal to 0, plug it inside here, and plug it inside there and see what you are getting. Now, if I'm plugging in a 0 here, I will get the square root of 0 plus 4 minus 2 all over 0. And if you look at this, it's going to be the square root of 4 minus 2 all over 0. The square root, as long as it is defined, the square root of this positive number is always going to give you a positive number. I don't want you to say that the square root of 4 is plus or minus 2. That's not true. The square root of 4 is always going to be a 2 here. So the positive one, so it's going to be 2, or the principal square root. So you have minus 2 all over 0, which is the same as 0 over 0. So we are actually having a 0 over 0 when we're evaluating this function at x is equal to 0. So what is the first thing that you need to do when you are actually having this function 0 over 0 at that particular point? I said the first thing that you need to do, you need to factorize. Now, if we are trying to factorize this, why are we factorizing? Because we have a 0, the 0 is associated with this x. We want to factorize so that in the numerator, we end up getting something that has some x in it. So once we have that x will cancel with this x, and then the problem will be gone, should be gone. But now, the problem we're actually having here is that we are actually having a root that is keeping this x from being cancelled with that x. So, whenever you have a problem of this kind, such that now you cannot just straightforward factorize, the second thing you need to try is rationalize. Remember that the main goal of rationalizing, we rationalize so that we can cancel the problem. So in this particular example here, if we rationalize this x, what will be the goal that we are going to achieve? This x is sitting nicely there. We need an x in the numerator so that it's going to cancel with this x here. Look into these other problems here. When we're evaluating this limit, we had this x minus 3, which was the only problem in the denominator. So we wanted to factorize the numerator so that we can cancel this x minus 3 in the denominator plus that one in the numerator. So we factorized the other part that did not have this part here. So the same thing here, we don't rationalize this part here. We rationalize the other part that seems to have this thing here that can be cancelled. So if you look here, I have an x. So the x is somewhere inside the root in the numerator. So I wanted to rationalize the part that is preventing that x from being cancelled. So I'm going to rationalize the numerator here. So I will end up having the limit as x approaches 0 of the square root of x plus 4 minus 2 over x. So to rationalize, you change the the sign that is between the two terms. So I have the other term that is made of root and the other term is 2. So I need to change that or find the conjugate of this particular part there. So this is going to be x plus 4 and then plus a 2. We take this part here that have a root as one term. You don't end up having to change this part because we want that whole thing that is inside the root. So we keep everything as it is inside the root. We only change the sign that is in front of this 2 here. And then we divide this whole thing by the same thing because it was not there. So we're going to have x plus a 4 plus a 2. Whenever, let's say, you just have a over b and we're saying rationalize the numerator, take note that this part here is the same as just a plus a 0 divided by b plus a 0. So when someone is saying rationalize the numerator of this, which means that you're going to change the sign between a and 0. So you end up having a divided by b times a minus 0, which is just a, and then you divide by a. So this sign here is always in between. So we're supposed to have minus 0 and minus 0 here, but minusing is 0, you haven't done anything. So to rationalize the numerator, this and that, rationalize the denominator, b and b. So we are done with that part here. So this is going to be the same as the limit as x approaches 0 of let me say this again. I'm gonna do this now. I'm gonna do this. Remember, the main goal was to cancel this x here, which was a problem because when I'm plugging in here and then I get a 0 in this whole thing, so I wanted to cancel that. So I am not going to simplify the denominator because I still need to cancel that part. So I'm going to have x and then times square root of x plus 4 plus a 2, and then in the numerator we'll have the square root of x plus 4 and then minus 2, and then I multiply by the square root of x plus a 4 and then plus a 2. And then I need to simplify now and say the limit as x approaches 0, and then I'm going to multiply this with that, and then I will end up with the square root of x plus 4 squared. I'm going to multiply this with that. I will end up having plus 2 times the square root of x plus 4, and then I'm going to multiply this minus 2 with that, so I'll have minus 2 square root of x plus a 4, and then I'm going to multiply minus 2 and 2. I'll end up having minus 2 squared. I divide. I am not going to simplify this because the main goal was to cancel this x, so I need to leave it there. So I will have an x, and then I'll have the square root of x plus a 4 and then plus a 2. Of course, if you look into this part and that part, they look the same except that they have opposite sign. So these two are gone, and now I'm left with the limit as x approaches 0 of the square root of x plus 4 squared minus 2 squared all over x square root x plus a 4 plus 2. Now, I have this nice thing here which I want to simplify. The limit as x approaches 0 of this squared will remove that root. I will end up having x plus a 4 minus 2 squared is a 4 divided by x times the square root of x plus a 4 plus a 2. If you look carefully into that, you will have the limit as x approaches 0. This 4 and that 4 are gone. I'm left now with x in the numerator. In the denominator, I have the square root of x plus 4 plus a 2. If you look carefully into this, now that x that was inside the root in the numerator now is exposed alone, and I can cancel it out with this x that I've been longing for to cancel. Now I'm left with, once I cancel one x, I still have the limit as x approaches 0 of 1 because x now is gone, divided by the square root of x plus a 4 plus a 2. And if you look carefully into this, I want to pick a value that is so close to 0, such that the calculator and the computer cannot really pick the difference between that number and 0. So if I pick 0, 100 zeros and put a 1 at the end, the calculator will just say, that's just a 0. Why don't you just plug it in as it is? So I have a 0 plus a 4 plus a 2. So the final answer we'll have is 1 divided by 0 plus 4 is 4. The square root of 4 is always going to be positive 2 plus 2, which is the same as 1 over a 4. So that is actually the limit we were looking for. Let's try another example. F, and I'm saying evaluate the limit as x approaches 0 of x all over the square root of x plus 1 minus a 1. Of course, the first thing that you need to do here, if I'm plugging in a 0 here, I will have a 0 divided. If I plug in a 0 here, I will have 0 plus 1 is 1, the square root of 1. The square root is always positive as long as there is no negative in front of it. If there is a negative, then you will have the positive number plus that negative. You will always have a negative. So the square root is always positive. So we have the square root of 1 is going to be 1 minus 1. So you have a 0. Whenever you have a 0 over 0, then the first thing is to factorize and cancel out the common factor. So if you look carefully into this part here, I have x, which is a problem in the numerator, and then now the problem here is caused by this whole part here. But the only thing that can be cancelled, I have to cancel x because there's only x there, so I need an x in the new denominator so that I can cancel. But the x that I need to cancel is inside the root. So I want to first expose this x so that I can cancel with that x. The only way to do that is to rationalize the part that has a hidden x in it. So I want to rationalize the denominator in this case. So this one is supposed to be the same as the limit as x approaches 0 of x divided by the square root of x plus 1 minus 1. Now, whenever I am actually rationalizing, I change the sign in between the two terms. So this term here that is inside the square root is considered as one term. So I am not going to change this because this is one term and then this is another term. So I'm only going to change this one sign. So I will end up having x plus 1 plus 1. So the opposite of this minus is going to be a plus. And then because that was not there, I need to divide with it again. And if you look carefully into this, what is important is that I needed to cancel this x out so that the problem can be gone. So this x here and that multiplying with that, we're not gonna simplify it. We're only gonna simplify the part that has an x hidden in it. So I'm going to have x in the numerator, and then I'm gonna have x plus 1 plus 1, and then in the denominator we'll have square root of x plus 1 minus 1 and have square root x plus 1 plus 1, and then this is the part that we are going to simplify or expand. So this one will be kept as it is because it has this x that need to be cancelled, and then in the denominator multiplying this with that, I will end up having the square root of x plus 1 squared, and then I multiply this with that, so I'm going to have plus the square root of x plus 1. I'm multiplying minus 1 and that, so I'll have minus square root of x plus 1. Minus 1 times positive 1 is going to be minus 1 squared. And now this is actually going to be, I'm going to have the limit as x approaches 0. I am not going to simplify the numerator because it has that x that we want to cancel as it is. And then in the denominator, this one and that one is gone because it has opposite signs, but it's still the same thing. So it's going to vanish. This one I have a square, so it's going to remove the root there. So I'll have x plus 1. And then I'm left with that minus 1 squared is going to be the same as minus 1. And then I have the limit as x approaches 0. The numerator, I am not going to expand it because it has that x that I wanted to cancel in the first place. 1 minus 1 is 0, so I'll have x in the denominator. Now, this x that was inside in the denominator that I wanted to cancel now is exposed. I can cancel them. And now I end up having the limit as x approaches 0 of square root of x plus 1 plus 1. Now, if you look carefully into this, all I need to do, I need to choose a value so close to 0 such that the calculator and the computer cannot pick the difference. And every time I am already choosing that value, I drop the limit. And then when I'm trying to plug that value, the calculator is going to say, listen, man, basically what is happening here is that the difference between that value, it's not that significant. Why not you just plug it in? So I end up just listening to it, and then I plug it in, and then I end up getting some nice values here. The square root of 0 plus is the same as square root of 1 plus 1, and the square root of 1 is always going to be positive 1 plus 1, which is just 2. So we have evaluated this limit here. Now, I want us to talk about this thing here when you're having f of a is equal to 0 over 0. The summary for that is as follows. That this is our summary. Our summary is saying, if let's say the question is saying evaluate the limit as x approaches a of f of x, where f of, if I take this value a here, I plug it in, I get 0 over 0. The first thing that you need to do is, which means you must always first plug in here, and then once you plug it in, if you are getting 0 over 0, then factorize and cancel out the common factor. Right. And then the second thing is, if this one cannot be done because the x or the t or the y you are trying to cancel is contained inside something that you think it can be actually exposed, what you need to do, rationalize that part that is giving you a problem. Rationalize the part giving you a problem. Right. So if let's say we have a route like we did in the previous case, then this one actually is actually going to be your ticket. But again, there are actually two more things that you can try. If this one is not working and this one is not working, you have to try these two methods, which we will deal with them at a later stage. For now, I want you to know this one and that one. Now, let's look into this. I want us to analyze, what do we mean by saying I have some f of a is equal to 0 over 0? The meaning behind. I want us to look at the meaning. Suppose I'm saying that I want you to deal with this function here, which is equal to x squared minus 9 all over x minus 3. Right. I want you to plot where x is not equal to 3. Because if it's 3, then it's not going to be part of that. I want you to plot this function. Of course, I don't know how to plot this function, but I know that f of x, I can factorize that and end up having x minus 3 and x plus 3 all over x minus 3. What this thing is actually saying here, whenever, if let's say I'm plugging in a 3 here, I get 0 over 0. Having 0 over 0 is meaning one thing. If you can factorize this and cancel the common factor, once you cancel the common factor, when you're plugging in a in that function, you are not getting 0 over 0 or a number over 0. It simply means that there is a hole at that point. Right. I'm going to write this thing down. If f of a is equal to 0 over 0, and after factorization and cancelling of the common factor, cancelling out of the common factor, f of a is not equal to 0 over 0, and f of a is not equal to a number over 0. So if this is not happening, and that is not happening after you've cancelled out the common factor, then there is a hole at x is equal to a. So that's basically what this means. Let me give you a nice example here. We said we had f of x is equal to x squared minus 9 over x minus 3, where x is not equal to 3. In other words, we have x minus 3 and x plus 3 over x minus 3. So I can cancel this thing out and say that actually this function is the same as x plus 3, where x is not equal to 3. So this function here and this function, we know that this is a linear. So this function have the same shape as that function. If I were to plot this function, I know that y is equal to x. Y is equal to x. It passes through the origin like this. Right, but now adding a 3, it means I'm shifting it up a couple of units, right? Oh, yeah. I'm just, what am I doing now? I'm just shifting that curve by a couple of units. This one that passes, so I have y is equal to x plus 3. This one was supposed to be like this, so this is y is equal to x. So shifting it 3 units up, so this is supposed to be 3. 3 units up, I end up getting that. Now, if you look carefully into this function here, at this point here, when x is equal to 3, then the output here was supposed to be somewhere 6, because if I'm plugging in here 3, I would get a 6. But knowing that when I'm plugging in a 3 here, I get a 0 over 0. What I meant is that if you are getting a 0 over 0, then this function is going to have the same shape, except that at this point here, the function is not defined, but the undefined is just a hole. That's what we mean. So if, let's say, you're having a 0 over 0, but after rationalization and factorization and cancelling of a common factor, you end up with something such that if I'm plugging in now a 3, I'm still getting a value. Then we know that at that point you must suppose to have a hole. That's what I wanted you to actually know more about in this particular lesson. And yeah, that's actually more important. I will stop there for this particular lesson and then see if we can proceed further as time goes by. Just a quick remark here. If you are evaluating a limit and you find out that your limit, when you're plugging in this value, you're getting 0 over 0, try 2 things. Factorize, cancel out the common factor, or if that cannot be done, rationalize and the part that is giving you a problem, and so that you can cancel out the common factor and then plug in, and then you actually have your limit. And if you are getting a 0 over 0, and when you are plugging in, you happen that you can plug in, then we know that at that particular point you must be having a hole. So the function must be having a hole at that point. Thank you very much.